Homework assignments due tonight at midnight. We will have a help session today at 12:55 at Beauregard 165. That's going to be sort of a standing thing, except for not next Friday, because what's happening next Friday? Yeah, so I'm really sorry. I don't like to move exams, and I think this is the first time that I've ever moved an exam, but I had a meeting come up, and had to move the exam for that reason. It's actually kind of good for y'all, because that means that we're not going to have Chapter 5 on there, so we probably could have finished. Chapter 5 is kind of short. We probably could have finished the whole thing. So we'll just have chapters 3 and 4. That'll be projectile motion, the second part of 3, or the lattice part of 3, and then forces. 1D forces, 2D forces. You're going to see our projectile motion prompts that we worked out, go over the concept test. You'll see some questions. Last time I think I had 5 or 6 from the OpenStax assignments, so go back over those. Not the real math intensive ones, but some of those that are a little easier math-wise. So help session today. We'll have a help session next Thursday. I sent a message out about that. I forget what time it was, 2 o'clock maybe, I forget. 3? Okay, yeah, 3 o'clock, 3 to 4. I think that's all. Yeah, am I missing anything? Yeah, you know. My meeting is actually on Friday. So I moved your exam to Friday because I'm having somebody come in and talk for my wife or Dr. Verma. Okay? Follow what I'm saying? Alright. It might be there for yours, but it's I have basically I have an exam it's the entire day for me. Okay, well let's do some more inclined plane problems. We're gonna throw in some friction on inclined planes today. Let's see, this was from an MCAT problem. First of all, actually, yeah, the MCAT problem here just asked, what is the frictional force, or how is the frictional force affected if the angle theta is increased? What happens to the frictional force if I increase theta? Well, what happens when you increase theta? Let's think about those things. Because it's actually a fairly complicated question when you get into the details. There are a couple different things that go on. When I increase theta, what happens to the static frictional force? And this will be the answer to the question. But remember, the static frictional force is always going to be equal and opposite to whatever force this is. Right? And this force comes about from what? This force is affected by what force? What physical force does this represent? It's actually a component of the force. What is that? The component of what force? The force right here is what component of our forces? It's our x component, right, of the weight, right? So remember when we're looking at this, we draw our axes, and then notice that this force, Fw, is some component. I'll call this angle phi. Fw is equal to Fw cosine of the angle phi. And so as I make theta bigger, that is, as I increase the angle of this inclined plane, phi actually gets smaller. And what's going to happen to this component of the force? Is this component of the force going to increase, or is it going to decrease? As I increase the angle of the inclined plane, what happens to the x component of the force weight? Does it increase or decrease? Let's ask that question first. A, B, it goes up or it goes down. That is, what happens to Fwx as you increase the angle of the inclined plane? Go ahead and get your clickers out. I'm having issues. I have to restart this. When you increase theta, what happens to Fwx? Alright, there we go. Does it increase or decrease? Feel free to ask your neighbor what they put. Right now we're about even that it goes up or it goes down. What happens to the x component of that force weight? Imagine a limiting case. Right, yeah, here. I'm asking, yeah, as this angle increases, what happens to this force? Does this force get smaller or does it get bigger as the angle goes up? Think of the limiting case of this, where the angle goes all the way up to the top. What happens to this force? The force that acts along the inclined plane. Has it gotten bigger or has it gotten smaller? All right. About 40 of you have the right answer right now. I'm going to stop at 58. 58. For 1 minute. Okay, good. A is the right answer. Imagine that if my inclined plane gets steeper and steeper and steeper, then my block, I'll have a force that's small there. It gets bigger and it gets bigger until it goes completely vertical, and then the component of that force that's along the inclined plane, it'll be equal to the weight, right? There will be no y component. It'll only be along the inclined plane. I'll be careful because I'm calling my x-axis along the inclined plane. So here, I would actually call this my x-axis, even though it's practically vertical. All right. So if FWX goes up, that means that FS will go up as well. Because Fs is always equal and opposite. That x component of the weight. At least on the inclined plane. Remember with the table? If I push on it with 50 newtons, the static friction will also be 50 newtons. If I push on it with 60 newtons, the static friction will also be 60 newtons. And on until it starts moving. Okay? Let's actually try working this. Let's see, we'll put some numbers in it soon, but let's just go ahead and look at this. We'll draw the free body diagram and sort of set up the equations for Newton's second law. So I'm going to draw my coordinate system right here. And now we're going to draw all the forces that are acting upon this block. I have the normal force. I have FWX, FWY. Now remember, these are going to be FW cosine of 90 minus theta. I called that phi. This is FW sine of phi. And then over here, this is my Fs. And so when I write out the equations like this, I can write out I can apply Newton's second law. Sum of the forces in the x direction equals max. Sum of the forces in the y direction equals may. And so that's going to be Fw cosine of phi minus Fs. That's equal to 0 because Ax is equal to 0. Bless you. And then in the y direction, what are the sum of the forces? We'll go ahead and write out the sum of the forces. And then what is the acceleration in the y direction? So do the same thing right here. And in fact, your steps are always going to be the same for all these force problems that you'll encounter. You might actually have some that are simpler because they're only in one dimension, but you'll still do the same steps. Draw your forces, draw your free body diagram, resolve your forces into their x and y components, and then apply Newton's second law. And that's where you get the equations that you'll need to solve. Y'all write this yet? The sum of the forces in the y direction? You got it? Let me write it up here. So it's going to be Fn, which is in the positive y direction, minus Fw sine phi, that's the y component of the weight, equals to 0. Now whenever we're dealing with friction problems, we also need to remember that Fs, I'm going to write it as an equality here, but we really know that's an inequality, right? It's less than or equal to. is equal to mu s times the normal force. So whenever we're dealing with friction problems, inclined planes or whatever, we need to remember this relationship as well. If it's static, then this is the formula we'll use. If it's kinetic, you just replace the s with a k for kinetic friction. You want to do one? Probably going to have one on the test, so let's do one. Here I have a block on an inclined plane, and I want to know what is the minimum mu s so that the block stays where it is. And so we'll go through all of our steps, choose our coordinate system, label all the forces. I draw my free body diagram or the vector diagrams and resolve all the vectors, and then I apply Newton's second law. And then once we apply Newton's second law, we'll see the formulae, and we'll decide on a mathematical way to solve that problem, figure out what is it that we're looking for. So I've already drawn the coordinate system. This is our x-axis. Remember, x is always along the plane of the incline. Y is always perpendicular to it. And I have all the forces labeled there as well. Let me, I'll go ahead and resolve these forces. Fn, Fs, and let's say that theta is 40 degrees. So I want you to now resolve Fw, and I'll give you about 30 seconds. Resolve Fw and place those on the x and y axes. What are the components, the x and y components of Fw? Alright, so I have Fwx is going to be, what do we use, the sine or the cosine for that x? Cosine. And do we use 40 degrees? No, you use 50, right? Because if you remember, I have a right triangle right here. So whenever you're doing the inclined plane, you always want to use this angle, which is 90 minus 40. It's only for the inclined plane. If we have other situations, usually our angle is already measured from the x-axis. I'll show you a problem like that in just a bit from last year's test. But on the inclined plane, you'll always take 90 minus that inclined angle. And so this is going to be Fw cosine of 50. And this is going to be Fw sine of 50. Okay, now we apply Newton's second law. We recognize that this is a static situation, so A is equal to 0. It's not accelerating. In fact, this one's not moving. Sometimes you'll see problems, and you'll say that it's moving at a constant speed. Whenever you see constant speed, that also means that the acceleration equals to 0. So it can be a static situation where it's, A is equal to 0, it's just not moving at all. Or if it has constant speed in the problem, then that's also acceleration equals to 0. That the velocity is not changing. All right, now let's apply Newton's second law. Sum of the forces in the x. I have Fw cosine 50 minus Fs. That's equal to 0. And then sum of the forces in the y. I have Fn minus Fw sine 50. Bless you. Equals 0. So now I have written my equations, and I want to know now what is mu. So let's take a little aside over here and explore the relationship between Fs, Fn, and mu. And in fact, this comes up, I think I gave a problem on the quiz, the homework assignment that's due next week. The coin problem, didn't I give y'all the coin problem? Y'all looked at next week's assignment yet? Probably not, yeah. It comes up next week, so Fs is equal to mu s Fn. So if I wanted a mu s, the only way that I can find mu, that's that coefficient of static friction, is I say mu s equals Fs over Fn. And again, let me just remind you that really this is not an equality, it's really a greater than or equal or less than or equal to, but I'm just sort of leaving that out. We'll assume that we have our maximum static frictional force. So I know that this is the case. I need to find out what is the ratio of Fs to Fn. But look, what don't I know up here? I don't know this, and I don't know this, but everything else I know. So I can solve this first equation for Fs is equal to Fw cosine 50. And then I solve this equation for Fn. Fn, excuse me. Fn is equal to Fw sine 50. And if I want to know mu, I say mu s is equal to Fs over Fn, which is equal to Fw cosine 50 divided by Fw sine of 50. And so look, my FWs, they cancel out. And it can give me the value for mu s, and I get 0.84. Remember, no units, which falls out here because these cosine, these trig functions, they don't carry units. And we cancel out our forces. There are no units on the coefficient of friction. All right? That's pretty similar to one of the problems that you have on the next homework assignment, the one that's due on, I think I made it on Wednesday. Okay? They don't give you the mass in that, but it turns out you don't need the mass in order to find out the coefficient of friction. It could be a test problem too. I might simplify it a little bit, make it as simple as possible, but still the same process you need to use. You'll definitely have inclined plane problems, both calculations and conceptual. All right, let's try this. What is the normal force acting on this block? What is the normal force acting on this block? And then if you get that one, go on to the next one, where I'm asking what is the coefficient of static friction. But here I just want to know the normal force. You're doing all right. About 30 of you have the right answers. If you're uncertain about what to do, ask your neighbor. Our folks here have the right answer, so ask around and ask them how they did what they did. It's similar to what we did on the previous problem. In fact, this is a very similar situation. We'll do about 15 or 20 more seconds. stop at 255, okay? 255. Just 5 more seconds. Hey, that's good. A is right. So I'm going to follow the same process. I know that y'all probably getting bored of this, but it's useful to go through these steps. Hopefully on the exam you don't have to go through all these steps, but as you're practicing, I recommend that you do. Draw my coordinate system, draw my forces. I have Fn, I have Fw, and I have to have some other force up here. It turns out that that force is going to be a static frictional force, but I have to have something that's holding it in place. Well, I don't have to. It can be accelerating down the inclined plane, but let's just say there's a static frictional force. And then recognize that this angle is 60 degrees. Then I can resolve those forces. I have Fn, Fw cosine 60, Fw sine 60, and then I have Fs. And so if I want to know Fn, look, if you have a static situation, then this force is always going to equal this force, because of the sum of the forces is 0. And so whatever is up has to equal whatever is down. So if I have a static situation, I can just forego writing those equations and just say, hey, Fn has to equal Fw sine 60. And that's equal to 85 newtons. 10 kilograms times 10 meters per second squared, which is 100, times sine of 60, which is 0.86, and that's 85. Or actually, I think I used 9.8 when I did this, but you get 86 with this. But use 9.8, you get 85. Okay, let's try the next one, and then we'll do some other sample problems. What is the coefficient of friction required to keep the block in the inclined plane, or between the block and the inclined plane, required to keep it in place? This is just like the previous problem that we worked. So you know what Fn is. Now you need to figure out what Fs is. And when you find Fs, then you can find mu, the coefficient of static friction. Again, if you're uncertain, ask your neighbor what they put. I'll remind you that we found Fn to be 85 newtons. Okay, doing very well. About 30 of you have the right answer. Ask around, folks. You're lost. Alright, let's do about 15 more seconds. Let's stop at 150. 150? Okay, A is right. A is good. Alright, so I know that mu is equal to Fs over Fn. We've shown that before. That just comes from this expression, that Fs is equal to mu s times the normal force. Excuse me. Goodness. So I have a cold this weekend. So I need to figure out what Fs is. Let's go back up here and we'll look at our diagram. I know that these two forces have to be equal and opposite. I know that because the sum of the forces in the x direction is 0. So this minus this is equal to 0. Or Fw cosine 60 is equal to Fs. And Fw is 100 newtons. That's 10 times 10. Cosine 60 is a half. So that's equal to 50 newtons. So that is my static friction for this scenario. And so I just say 50 divided by 85, and that's equal to 0.6. So A is the right answer. You'll probably see a problem that's broken down into 2 or maybe even 3 parts with the inclined plane, just because, you know, one problem, it takes you a long time, there's sort of a lot of different parts to go into. But you'll probably see something like this, where you have to work through the inclined plane that has friction on it, and it could be static or it could be a dynamic problem. And we'll look at that next. Okay? I think you had a blank page, so let's go back up to that previous page. Now let's think about dynamic problems. Really, we've done some dynamic problems, but not in 2 dimensions. And so let's do a dynamic problem. And by the way, guys, I think that next week we're going to do a lot of test prep, because I really want Friday's exam to blow out of the water. I want y'all to do really well on it. So Monday and Wednesday, we're mostly just going to review. Like, we're not going to go on to the next chapter, because I think that y'all are still struggling a little bit with projectile motion, and I definitely know that you're struggling with 2D forces. So we'll revisit a lot of things. If you feel like you've got it, like you think that you're going to do fine on Friday's test with no extra work, then that's fine. Just don't come. We might have a few clicker questions, but not very many. Okay? All right, so let's do a problem with dynamics. Just going to make it up on the fly here. So let's say that I have an inclined plane. Let's say that this angle is 30 degrees. And I have a block here that is 10 kilograms. And let's say that this thing is accelerating down the inclined plane at 1 meter per second squared. It's sliding down the inclined plane. And I want to know, what is mu? What is the coefficient of friction? Is this going to be mu s or mu k? It's going to be mu k, right. So what is mu k? All right, so what I need to do here is the same thing I do every other time. I draw my coordinate system like this. Then I draw the forces that are acting on this object. Well, I got my normal force, I got my weight, and I got my kinetic friction, Fk. Fk is up the inclined plane because the object's sliding down the inclined plane. Now remember, our frictional force, it always opposes the direction of motion. Or in the case of static friction, it opposes the direction that the object would tend to move. Like if I try to push it in this direction, the static force will be the opposite of that. So here I want to know, what is mu k? So I start with this. I say, now I resolve my vectors, just like I've been doing. Fn is already on the y-axis. Fk is on the x-axis. And then I have Fw sine 60. That's 90 minus 30. And Fw cosine 60. Okay? Now, remember, mu k is just like it was for mu s. Mu k is equal to Fk divided by Fn. Because that same expression still holds for static and for kinetic friction. It's the ratio of my force, my frictional force, to my normal force. But where this differs is when you start to write Newton's second law. So the sum of the forces in the x direction is going to be Fw cosine 60 minus Fk equals to 10 kilograms, that's the mass, times the acceleration. So it's no longer equal to 0. It has this non-zero value. And then similarly, sum of the forces in the y direction, Fn minus Fw sine 60 That's equal to MAY. What is my acceleration in the y direction? Very good. It's equal to 0. Right? That's why we draw our x-axis parallel to the incline, so that we know that the thing isn't moving in the y direction. So we can always say that AY is equal to 0. I was trying to trick you, but y'all are too slick for that. All right? So that's equal to 0. And that will always be the case for inclined plane problems. So some of the forces in the y direction will always be 0. Otherwise, the object is coming off of the inclined plane. It's accelerating off of it, and we don't want that. All right. So now let's see. What don't we know? Well, we don't know Fn, and we don't know Fk. So I mean, this problem works basically the same. The only difference is that I have this acceleration. And by the way, I could ask you, what is it accelerating at? Right? I could ask you that. You'd work it very similarly. It's just what you're solving for in the end would be different. But you would work up to this point exactly the same. In fact, all of your problems, you work up to this point exactly the same. All right, so let's just put some numbers in here. So Fk is equal to Fw cosine 60. What is this, 10 kilograms? So it's 100 newtons cosine of 60 divided by, oh shoot, what am I doing? No, that's not right. I'm sorry. It's not right. Not divided by. 100 cosine 60 minus 10 times the acceleration, which was 1. What does that equal to? 10 times 1? I know that's 10. What is this whole thing equal to? Anybody know? It's 40, right? Yeah, so 40. So that's equal to 40 newtons. And then similarly, we do that over here, where it's just Fw sine 60. That's equal to 86 newtons. And then to find mu k, we take the ratio of those 40 over 86. And that's equal to about 0.5. Okay? Whatever it is, I don't know what it is. Let me show you a different question. This comes up on an old test, and we'll work through a problem like this soon. But let's say that I have an object. It's just sitting on a flat surface like this. And let's say that the mass of this object is 5 kilograms. Let's say that I'm pushing down on this object with a force equal to 10 newtons. And this angle is 30 degrees. What is the normal force? What's the normal force? If there was no force pushing down on this object, what would the normal force be on this 5 kilogram object? 50's right. It would be equal to the weight, right? And that's usually the case, that the normal force is equal to the weight. But in this case, we have something extra going on. We have a force that's being, somebody's pushing down on the object. And does that cause the normal force to decrease or increase? Right, increase, right. So the normal force will actually go up. So I know that my normal force is bigger than 50 newtons. Or, yeah, the normal force is bigger than 50. Is it going to be bigger than 60? It would be equal to 60? No, it's going to be somewhere between 50 and 60. Well, how do you know that? Well, look, if I was pushing straight down with 10 newtons of force, then my normal force would be equal to 60. Because all that 10 newtons is going in the y direction. But here, only part of this force, this 10 newtons that you're pushing down with, is going in the y direction. Part of it's going in the x direction. And part of it's going in the y direction. Let's stick to what we're doing. Let's draw our coordinate system. I'm going to label all the forces. In this case, I have a force F that's 30 newtons, or 30 degrees rather, from the x-axis. And I have the force weight. And then I also have the normal force. And that's all I have. I want to know what that normal force is. But I know that that normal force is going to be somewhere between 50 and 60 newtons. Somewhere bigger than the weight, but less than the weight plus the 10 newtons. This is F equal 10 newtons. The force weight is 50 newtons. That's 5 times 10. I resolve my vectors. Fn, F cosine 30, F sine 30. Notice that I didn't do 90 minus the angle because the angle is already measured from the x-axis. And that's it. Oh no, it's not. And then Fw. Sum of the forces in the y is equal to 0. So that's going to be Fn minus F sine 30. Be careful, another negative, minus Fw equals to 0, because F sine 30 and Fw, they're both in the negative direction. And then I solve for Fn. It's going to equal to F sine 30, that's 10 sine 30, minus, or plus rather, Fw, which is 50 newtons. That's 55 sine of 30 is half. Yeah, so it's 55 newtons. Alright, so that's my normal force. If I was told that there's a frictional force applied here, then I can now figure out what is that frictional force, because I know what the normal force is. Let's just say that. Let's say, what if mu k was equal to 0.1? What is the acceleration of the system, or of the block? If mu k was equal to 0.1, what is the acceleration of the block? Well, then we need to revisit our vector diagram, because now we're going to have an extra force up here. We're not just going to have these three forces, we're going to have another force that is in this direction. And that's going to be our Fk. This will be Fk. Fk again. And then I want to figure out what Fk is. Fk is mu times our normal force, which is 0.1 times 55, or 5.5 newtons. And then we say the sum of the forces in the x direction is equal to F cosine 30 minus Fk. And that'll tell us the net force that's acting on this object. That's going to be, what did I say F was? 10 newtons, cosine 30, minus 5.5. And so that's equal to 8.6 minus 5.5, or 3.1 newtons. Cosine 30 is 0.86. Alright, so now how do I get the acceleration? Well, I know the mass, and now I know the net force. And so the acceleration is just F over m. The acceleration is F over m. It's 3.1 newtons over 5 kilograms. And that is about 0.6 meters per second squared. Roughly. Somewhere close to that. Okay? You could have a problem like that. It'd be in pieces. I wouldn't ask you all those things in one problem. But, yeah, Gavin? Yeah, of course. The one up here, the inclined plane?
Yeah. So, for finding vector one, that's the acceleration of the block going down the inclined plane.
Yeah. I think you're asking that question
Yeah.
because
For kinetic friction, 100 newtons times cosine 60 minus 10. That's the 1 meter per second.
that's right. Yeah. I don't think this is why you're asking the question. I don't think just being clear on this stuff. But why didn't I put this as -1? It's going down the inclined plane, isn't it? So if it's going down, it should be negative, right? It's going in the positive x direction, right? So be careful. I don't think I'd put that little complication on the test, but if this thing was going up the inclined plane, that acceleration would be negative. You pre-med students, they'll do something like that on the MCAT, but they're not nearly as nice as I am. I don't know if y'all know that. Like the MCAT people, mean. Me? Sometimes I'm mean, but not always. Like usually I'm not. Okay? It's a tough test, man. MCAT. You think my test is hard? Take the MCAT. Right? Am I right or am I right? It's tough. But y'all can do it. Like we have students that do really well on it. And that's who y'all are. You can do well on it. Okay. Let's do some more of our quicker questions. Hopefully we'll wrap these up today. And then like I said, next time I want to spend a lot of time on test prep. Yeah.
Okay. Max is 5 kilograms per block. So you're also pushing that way. So that doesn't add to its mass. Like, does it add to the force of friction?
It doesn't add to the mass, but it adds to the normal force.
Okay. So that's why it's like factored into the.
Right. The normal force is bigger. I know what you're thinking, Nick. What if we just made the mass bigger? But you gotta follow a process here. You gotta follow the process always. And the process is always the same. But it's just you sometimes get to a different
So
answer.
by like making the normal force bigger in the equation, you're accounting for the force that's bigger.
That's right. He said by making the normal force bigger, when you calculate the normal force to be bigger because of that force that you're pushing down, then that accounted for the added force. Yeah, so you kept the same mass. So as I was saying, next week, I'm probably going to spend some time on old test questions. And I know it's useful to have them printed out. So I think fall 15 is in your workbook. If you want to print out fall 16 and maybe fall 14, and maybe even as far back as fall 13, then that might be useful for you because we'll probably address some of those and go through them and say, gosh, I wish you'd really go over this question. And if you have particular questions like that, then we can do so. So I'm not really considering it a help sessions per se, but we're going to spend a lot of time reviewing stuff because I think everybody needs that. Most of you need it, right? All right. You might know which one we left off at. 4.9a. We did this one or we didn't do it? Okay. This is a good question. It's moving upward at a constant speed. How are normal force and weight related? All right. Ask your neighbor what they put. Oh, you're doing all right, actually. About 45 of you have the right answer. I'm going to stop at 118. 118. Okay, well that's not that great, but B is the right answer. That if I'm moving up at a constant speed, that means the acceleration is 0. And if I were to draw my force vectors, I have one force going up, one force going down, that's the weight. This is the normal force. Because A equals 0, those two are going to equal. The sum of the forces in the y, Fn minus Fw, is equal to MAY. And A is 0 in this case. Or what if, same situation, but now it's accelerating upward? What's the relationship between N, the normal force, and the weight, mg? Right, doing well, about 50 of you are on the right track, so check in with your neighbor. Not following. Y'all know your neighbor? You know your neighbor? Do you? Okay, let's stop at 58. 58. Okay, good. A is right. N is bigger than mg. So, same idea here. This is my normal force. This is my weight. The sum of the forces in the y direction are equal to MAY. In this case, MAY is not 0. So that's Fn minus Fw equals MAY. So Fn equals Fw plus MAY. You got that extra. And by the way, if it's going down, then this becomes a negative number, and so it becomes Fw minus MAY. So if it's going down instead of up, then my normal force would actually be less than the weight. And then, of course, if it's in free fall, then you're weightless. That's what it means to be weightless, that there is no normal force pushing on you. In fact, you ever use the scales? You ever use a scale, like measure your weight? Yeah. Really what the scale is measuring is not your weight, but it's measuring the normal force. It's not measuring your weight. So next time you go to the doctor and they want to measure your weight, jump up there and like, let's see what my normal force is today. Because it's not your weight, it's your normal force. All right. You have a physics student pulling or pushing a sled. Which of these is the normal force greater? Case 1 or case 2? That is a snow sled that is on the slide. In some parts of the country, they get frozen water that falls from the sky onto the ground, and then they can push things across. All right, let's stop at 50. 50. Oh, sorry, let's see. Yeah, A is the right answer. The one where the normal force is greater is the one where you're pushing down. Just like the problem that we worked before, if you're pulling like this, it actually makes the normal force less, right? If you're at full, then you're pulling up a little bit, and so the normal force increases. So I never understood, like in the grocery store, how do you push your cart? You push like this, right? So you're pushing down, and so the normal force of your cart is actually bigger than just the weight. So really what we need to be doing is we need to pull the cart like this, behind us. You know, think about that next time you go to Walmart or Rouse's, wherever you go. For which of these cases is the normal force greater? Case A, case B, both the same, that is the normal force is equal to the weight. Both the same, it's somewhere between 0 and the weight, or both the same, the normal force is equal to 0. Remember what happens on the inclined plane. The normal force is often equal to the weight. What happens on the inclined plane? Let's stop at 110. Okay, A is right here. Because on the in A, our normal force is equal to the weight. They're equal and opposite. Acceleration is 0. But here in B, my weight is here, and my normal force is here. So only a portion of the weight, the y component of the weight, is equal to the normal force. Sorry, this should be an N. There's our vector diagram. So the normal force is equal to the y component of the weight. In outer space, bowling ball and a ping pong ball attract each other due to their gravitational forces. How do those magnitudes of the forces compare? I haven't told any jokes today, I don't think. I want to tell at least one. I have a good one. All right, let's stop in about 10 seconds. We'll stop at 45, 45. Okay, C is right. They exert the same force. The forces are equal. Remember our universal law of gravitation? It was that G equals m over r squared. This force gives F12, but it also gives F21. So both masses affect the force, but they affect them the same because both masses affect the retractive forces. So since m is here both times, it's going to be the same force. You can also think of Newton's third law, that this is an action-reaction force, that these two forces are equal but opposite. Let's do one more, okay. How do their accelerations compare? So the same situation, they've had the same force, so F12 equals F21, but how do their accelerations compare? All right, next time we'll wrap up these questions and we'll do test prep. Okay, I'm going to stop at 30. And the answer is E. They're opposite, but the ping pong, which has a smaller mass, accelerates faster. And then the small, A is big. I'll save that joke for next time.